Welcome to Spring LIB.
Part A of the given problem, we use a Lorentz transformation equation to write delta t dash is equal to gamma times delta t minus v times delta x divided by c squared, and this will be gamma times delta t minus beta. We wrote v and c in terms of a beta speed parameter, delta x divided by c. Substituting a values, we get here gamma times delta t, which is 1 times 10 to the power minus 6 seconds minus beta times delta x, which is a 400 meter, divided by the speed of light, which is 3 times 10 to the power 8 meter per second, where the Lorentz factor itself is a function of beta. We get so this is an expression for delta t dash for part A. For part B, a plot of delta t is a function of beta, as you can see from this equation, in a range of beta greater than 0 and less than 0.01. We can write this plot in the following way. So let's say on x-axis we have a beta, so this is 0.01, this is our 0, and this is a 1. This is our delta t dash. Then we see the equation, the line will be straight here, constant up to 0.01. We note that the limits of the vertical axis are, so here will be plus 2 microsecond, and here in this way, here in opposite side, this will be a minus 2 microsecond. We also note that how flat the curve is in this graph. The reason is that for low values of beta, Bullwinkle's measure the temporal or measure of the temporal separation between the events is approximately as hours, which is namely 1 microsecond. There are no non-intuitive relativistic effects in this case. When we plot the delta t, so when we plot delta t here, so let's say here is again our beta, and here is our delta t dash. For the values which are 0.1, beta greater than 0.1 and less than 1, we see from this is 0, and here it will, so let me use another color, from below 1 it will cross here, and then it will flatten down. So the point it crosses here is around 0.8. So here is the 1, and this is 0. Here is the 1, and here is our 2 microsecond plus 2 micro, and here is our minus 2 microseconds. Part D of the problem, setting our, so this was for C. For part D, setting delta t dash is equal to gamma into delta t minus beta delta x divided by c. From here, substituting the values for so gamma into 1 times 10 to the power minus 6 seconds minus beta 400 meters divided by speed of light 3 times 10 to the power 8 meter per second is equal to 0. Setting this is equal to 0. Gives us a beta value, which is c delta t divided by delta x. So substituting the values, we get here approximately 0.750. Part E of the problem, from the graph that we shown in part C, As we increase the speed, the temporal separation according to Bullwinkle's is a positive for the lower values and then goes to 0, and finally as the speed approaches the speed of light becomes progressively more negative, as we can see here. So when its speed increases it becomes more negative here. For lower speeds with delta t dash greater than 0, we can write delta t a dash is less than t b dash, which implies 0 beta less than 0.750. According to the Bullwinkle, event A occurs before event B, as we just observed. For the part F, for the higher speed, the delta t dash is less than 0. So for this t a dash will be greater than t b dash. That is 0.750 less than a beta, which is less than 1. According to Bullwinkle, event B occurs before event A, the opposite of what we observed. For part G, the answer is no. Event A cannot cause event B, or vice versa. We note that the delta x divided by delta t is 400 meter divided by 1 microsecond, and this gives us 4 times 10 to the power 8 meter per second, which is greater than the speed of light. The signal cannot travel from event A to event B without exceeding the speed of light, so the causal influences cannot originate at A, and thus they affect what happens at B or vice versa.